Thanks everyone for joining our webinar series. For those who are new, ClimTip is a European Union funded project on uncertainty-aware quantification of climate tipping points. And we do this webinar series as a platform for various level scientists to share their research on various aspects of climate tipping points. And today we have a special guest, Natassa Romanou from Columbia University, which is part of the NASA Goddard Institute for Space Studies. And she will be talking about extreme events, the relationship between extreme events and tipping systems and their potential to contribute to such tipping events. A few words about our guest speaker. Natassa Romanou is a research scientist at NASA GISS, and she's also an adjunct associate professor in the Department of Applied Physics and Applied Mathematics. And her background is in physics and physics oceanography. And she's also one of the lead authors of the next IPCC assessment cycle. The Working Group I will have a special report on tipping points, and she's the lead author there, and that's why we're especially excited to have her here as that work on IPCC report's next cycle commences. So without further ado, Natassa, you're welcome.
Yes, thank you very much. Thank you for the invitation, particularly in this group of people. You are working on tipping systems and a lot, and I would really like to hear your input. In this talk, I will be discussing extreme events and how these are contributing to tipping systems. Of course, there is the reverse interaction where tipping systems affect or promote and establish new extreme events, but this is not the part of this work. Oh, I cannot. Okay. So the overview of my talk is, of course, we have a background of global warming, which is accelerating non-stationary forcing of the Earth system, which is pushing the system to forced trends. This global warming enhances and accelerates even the stochastic variability, interacts with what we call stochastic variability. Our tools to explore these and understand these interactions are numerical models and machine learning. Of course, we have evidence from observations and paleoclimate as well, but the talk will be focusing on numerical simulations and machine learning. The stochastic variability in models, how we express it in models, how we understand it in models, is what we call internal dynamics, interactions of large-scale modes of variability, for example, the Arctic Oscillation, the ENSO, the Pacific Decadal Oscillation, or the Southern Annular Mode, with local, how these interact with local dynamics and give rise to climate extremes. Under current climate warming projections, we know that such extremes will be becoming longer, more frequent, and more intensified. And tipping systems are often studied as singular bifurcations under some gradual forcing, usually imposed in numerical simulations. But the two interact, the stochastic variability and the tipping systems interact. They are amplifying or damping nonlinearities, exacerbating trends, and leading to abrupt transitions. And so in this talk, I will be talking about these noise-induced transitions, which are promoted by stochastic variability, what we call stochastic variability in the models. And I will give some examples from the terrestrial carbon cycle, the cryosphere, the ocean circulation, and then we will discuss how these stochastic transitions may be happening earlier and at lower levels. And that's very important because that will lead us to understand how the timeframes of occurrence of tipping in the tipping systems might happen if it is moving closer to us or not. So, as I said, we have the climate change, which is happening all around us, and we are witnessing it and we are measuring it. And of course, that leads to both increased frequency of intensity and duration of extreme events, extreme weather, that has been very well documented. And of course, climate change also pushes the system closer to tipping points. So that means transitions, critical transitions, where the system will start from a stable state of the last few hundred and thousands of years, and then it might move into a new stable state, which is, of course, a very different climate. And there is a positive feedback, but I will try to show that there is evidence for positive feedback between these two, the increased frequency of extreme events and the nonlinear response of the system to the warming, the tipping. So scales of tipping systems. There are, on the left-hand side, you see a graphic, a very nice graphic from TPSM, which is showing how, what are the main tipping elements or tipping systems in the Earth system, in the broader Earth system. This is the overturning circulation in the North Atlantic, permafrost, boreal forest, and of course the ice sheets, Antarctic ice sheets and Greenland ice sheets, and the tropical forests as well. Of course, tipping happens in every scale. Of the known world, both temporal scales and spatial scales, from the minutes and the microscale all the way out to decadal and global scale, millennial scales, decadal variability, and so forth. But we are not going to focus on everything because, as I said, tipping can happen at every time scale and spatial scale, but we are going to focus in the longer time scales in decadal variability, and basin scale and larger, which will represent impacts to the climate system and will affect millions of people when they are happening. In a recent paper, Armstrong McKay and his colleagues, they developed, they put forward this I think, a very important map which shows the different tipping elements across the Earth system, and they provided the horizons, both in global warming thresholds but also in temporal scales. The global warming thresholds where these tipping systems are going to, or the critical transitions are going to happen in these systems. So, for example, if we look here at the Labrador Sea, the subpolar gyre in the North Atlantic, as well the Greenland ice sheets and the West Antarctic ice sheet, these are emerging. These are expected to happen. They're considered that they can happen at very low, at lower global warming thresholds of about 2 degrees Celsius. And then as we move to other systems, for example, the Atlantic meridional circulation, which is a broader system than the subpolar gyre collapsing, as well as boreal forests and permafrost, these have a much longer scale, threshold for happening around or above 4 degrees Celsius. Of course, there is a large uncertainty in these thresholds extending from very low temperatures of about less than 2 degrees, could be around levels of global warming that we will be experiencing in the next few decades, or going further beyond 4 degrees. As I said, so the point is that we have an idea now of this global warming level, as well as some kind of idea of thresholds, temporal thresholds, where these elements are going to be materializing. Now, at the same time, we know, going back to SROC 2019, which is an influential report about climate change, that extremes are happening and they are accelerating. They are becoming stronger and more frequent and more and longer as climate change progresses. And these, and it's not single only extremes, which are something in the future, in the present and in the future, is also compound extremes, meaning that extremes that are happening at the same time, like, for example, heat waves together with droughts and wildfires, or marine heat waves together with ocean acidification and deoxygenation. And the singular events themselves might have a much delayed thresholds, but the compound extremes also, they can have a much bigger effect in the systems and much earlier. And of course, extremes have immediate impact on populations and socio-ecological systems, because these are, of course, affecting different regions much faster. And they are already happening in the system, and we are witnessing them, and we are witnessing how they are changing. In a recent study by Catopondi et al., they showed that these distributions of extreme events are changing around the globe, and they are changing differently across different geographical regions. For example, in the Arctic, we have the entire distribution shifts to the right with about 1.2 degrees warming in the mean state. And at the same time, the tails of the distribution are also themselves expanding. Similarly, in the Western tropical Pacific, huge changes are taking place, but not so much in the Northeast Atlantic. The important point of that study that I want to highlight is that the marine heat waves, which are increasing in intensity, etc., and this has been found by others like Desser et al. 2024, they are promoted, and their intensity is changing much faster in areas where internal variability is playing a big role. What I talked about before, the combination of different large-scale modes of variability and local scales of change. And for example, we see that for the marine heat wave intensity at the end of the century, the projections of marine heat wave intensity change by the end of the century, the biggest contribution comes from internal variability, about 30 to 40 degrees. And in the North Atlantic, especially the western side of the North Atlantic, 80% of the marine heat wave intensity change is coming in from internal variability. So there is clear evidence from numerical simulations. This is all numerical simulations, of course, projections. The numerical simulations are showing that internal variability plays a big role at how these extreme events are developing and how they are contributing to the mean state, but also the extremes of the distributions. And that motivated us in a study of extreme events contributing to tipping elements and tipping points. And we looked at basically how these are affecting, how the extreme events and where they could play an important role affecting the tipping systems. And I have to say here that not always we have positive feedbacks, meaning that the extremes are accelerating towards the tipping threshold. Sometimes extremes could potentially lead us or counteract the progress towards a critical transition. So in the top diagram here on the right, you see the main tipping elements, like, for example, the boreal forests and the Atlantic overturning circulation and the Amazon forest and the ice sheets in Antarctica. And you can see we have superimposed drivers of extremes, the types of extremes which could be affecting it. Like, for example, in the boreal permafrost, heat waves and wildfires play a big role. But in the Atlantic meridional overturning circulation, warming of the ocean, marine heat waves, sea ice extension extremes, and transport can play a role. In the Amazon, for example, wildfires, droughts, and heat waves, and so forth. And these all can lead to very important types of, and these are the ocean, or let's say some of the tipping systems. And here you can see other tipping systems, like, for example, the Sahel forest or the boreal forests and the low latitude corals, how they are affected by deoxygenation and acidification. So as we move forward, we will get into the first example, which is the Amazon the Amazon rainforest dieback. Here we have a compound drivers which come from human disturbances like fossil fuel emissions, obviously, and the warming that they ensue, land use change and deforestation and land management, which lead to atmospheric CO2 increase, and that leads to warmer temperatures in the atmosphere, and of course, droughts. But these both lead to fires, wildfires, but also we have managed fires as well, fires which can play a big role and lead to forest mortality, and that can lead to a decreased net land carbon sink, regional carbon losses, which are very large, and that feedbacks, of course, back into the CO2 increase, thereby enhancing, essentially, the effects of global warming. Now, this particular study, for example, from Flores et al. Showed that there are plausible ecosystem trajectories which are basically not looking very good because there are different types of positive feedbacks, which are shown here in these loops, where they can reinforce essentially the dieback of the Amazon rainforest. So, for example, in a white sand savanna type of scenario, we have here the lower trees which are being affected by fires, and soil erosion plays a big role, degradation of the vegetation, seed limitation that leads back to lower tree cover, and this cycle is reinforced. In degraded open canopy, which we can see on this side of the diagram, in the middle section of the diagram, you can see that extreme droughts and fires together now affect low tree cover, again by promoting fires and the invasion of alien grasses in this area, which affects soil degradation, seed limitation, and then reinforce the dieback of the Amazon. And in a degraded forest, warming together with extreme droughts and deforestation and fires now will lead to deforestation, fires, and the invasion of opportunistic plants, which will limit seed limitation, will not allow the forest to rejuvenate. And of course, the Amazon dieback is continued. Now, jumping to higher latitudes in the Arctic sea ice, in the Arctic area, we are looking at sea ice extent. Sea ice extent variability is characterized, and you can see this in these three diagrams here, which represent numerical models from the Canadian Earth System model, the NCAR climate model, and then the suite of CMIP5 climate simulations. You can see these, the Arctic sea ice extent variability between 1960s approximately and today, and the current climate. It wasn't today when they were running the simulations. But the important point is that in these diagrams, the black line is the sea ice extent from observations. And that comes from the Kirchmeier-Young paper, 2017. And they showed that all the models, which are shown here in blue, this is the all forcings model. They're looking at other forcings too, but like single forcings. But here, please focus on the blue shaded line and the blue line. These are climate simulations of Arctic sea ice, and you can see that how little of the variability the models are projecting in the ensemble mean. Very little, there is a lot of variability, obviously, in the observations, which is not captured in the Arctic sea ice extent model simulations, especially when we are looking at the ensemble mean, and this is very important. Now, this is not only the Arctic sea ice where models do not have internal variability representing what we are seeing in reality. AMOC, for example, simulations of the overturning circulation in the suite of CMIP6 models showed that the internal variability that the models show in terms of the AMOC is very low compared to observations, is extremely low, in fact. And that, of course, needs to be taken into account when we are considering the model's ability to project AMOC sensitivity to extreme events and obviously its sensitivity of crossing possible tipping points. Okay, so here is, with that in mind, here is a study that we conducted a few years ago, and actually it was a novel effect in climate models. Up until that point, subsequently, it has happened in other models as well, but up until that point, in order to induce AMOC, the Atlantic Meridional Overturning Circulation collapse, we had to impose a external freshwater forcing, hosing, as we call it. And typically large amounts of fresh water had to go into the subpolar gyre and sometimes even the entire North Atlantic basin in order for the models to get the AMOC to collapse. It's too stable. It was too stable to external perturbations. We don't always know why. It's a very important and interesting question, why the models are so resistant to freshwater forcing, but it is what it is. In this particular simulation, which is the SSP-245 extended simulation with the NASA GIS climate model, what is the extended 245? The extended 245 is the 245 scenario, but extended beyond 2100 with slowdown of the warming and then or the slowdown of the concentrations in the atmosphere of CO2 and then slow some decline. So there's strong non-linearity which is imposed in this part of the curve, right? And that translates, of course, as a forcing into the model. So what we saw is that right after 2100, about a decade after 2100, in this simulation, which we did with 10 ensemble members, identically forced, some of them, 8 of them, recovered. The AMOC recovered. It was declining throughout the 21st century, and then it started to recover as the forcing slowed down. But in 2 of the ensemble members, it didn't. It actually collapsed. And it collapsed by 2200. It had reached what some people consider a critical threshold for AMOC. It collapsed. It remained collapsed for several 800 years, approximately 800 years, and then recovered, obviously. But for what we are interesting here for the purposes of this study here, and in general for human timescales which are relevant to humans, it was a collapsed AMOC and would have detrimental effects if it remained collapsed for several hundred years. So we studied very thoroughly why this was happening in our models, and what we realized was that it was happening because of extreme variability of the sea ice transport that comes out of the Arctic Ocean into the subpolar gyre through the Denmark Straits and into the Irminger Sea, which is one of the main regions of production of deep water formation in the North Atlantic in our model, and which was the only site of convection that remains in the 21st century after the Labrador Sea has shut down. The Labrador Sea, we know, and other models are showing, if we continue warming, it will be covered by ice, it will shut down the convection. The Irminger Sea in some models remains open, in some models it doesn't convect. In our model is our main convection site, and that is what promotes some of the return of the recovery of the AMOC after the strong decline and as the forcing is changing. So here is a plot that shows the sea ice transport across the 80 North, and that's 80 North, but also that lower into the subpolar gyre, which shows that, for example, these ensemble members, they have much less variability. this is averaged over the 8 ensemble members, whereas the 2 that remain have important variability, which is happening a little bit before the bifurcation, if we call this bifurcation, the bifurcation time of our AMOC. So that was an interesting study that showed that our model, the NASA GIS model, the AMOC is very sensitive to internal variability, to the variability of sea ice, obviously to the variability of any type of freshening at the surface. And that is an effect that later on was seen in other models, lower complexity models, the Perner et al. Study, but also with CSM, Van Vesten and et al. Study of 2025. So that's that. That's what is happening in the North Atlantic, where we see evidence, numerical evidence, obviously, of the sensitivity of a tipping system to extreme events. Now let's go to East Antarctic. Now we see observational evidence. Here in Antarctica, remember, the ice sheets of the Antarctic are considered the most susceptible, or the soonest susceptible to crossing a critical threshold. The West Antarctic ice sheet first, later the East Antarctic. Here in the East Antarctic ice sheet, there was documented an important collapse of the Conger-Glenser ice shelf in March 2022, which was linked to intense atmospheric river variability in the area and marine heat wave, which persisted for many days. And that led to huge precipitation values. This is a percent of March 2022 precipitation above the recent state. So 90% above the recent state. And also the bottom plots show the melt that was associated with this, with the precipitation. There was a large there were large melt events that happened a little bit below a little bit below the Conger ice shelf, but nevertheless the conditions were very similar there as well. The Conger ice shelf is here as well, of course. And that led to an extensive melt that was probably the largest, the most extreme melt that we saw in satellite observational era since 1979. Now, of course, we would be amiss if we didn't go back to paleoclimate evidence. I'm not an expert in paleoclimate, but there are many papers which are showing evidence of climate flickering. Climate flickering meaning these transitions, these extreme and quick, fast, very fast changes between states between extreme events in paleoclimate record. And this is a paper that documented the associated determination of the African humid period 600,000 years ago, 5,000 years ago, in Sahara, when Sahara was actually green and transitioned into the super arid condition that it is today. So measurements from records, paleoclimate records from the Ethiopian Rift region showed that this was a period where was preceded by the flickering, meaning that changes between drought and wet extremes in the region, floods and droughts, very quick, within 160 years. They were happening every 160 years, and that climate flickering was considered as an evidence of the transition of the Saharan region transitioning into the new climate state. Right. So again, with going back to the NASA GIS climate model, I'd like to show you some very fresh results for where we are looking at mitigation and climate intervention pathways and what could that do to tipping. Well, there is literature on that. There's a very big interest, obviously, on that, if we want to understand how these mitigation pathways of climate intervention are going to affect our climate, and if they are effective in what they are claiming they want to do. And what we are looking at some idealized scenarios. We are looking at the CMIP stabilization scenarios where we are switching off emissions completely. So it's not a very realistic scenario, but it is a scenario where we are looking at the response of the system to zeroing out emissions. This curve here is the black curve here is the 1% run, off of which we turn off emissions at different levels of CO2 going out emissions of 800 petagrams carbon all the way to 2000. So, and this is the CMIP stabilization scenarios now here. We are looking at the main CMIP scenarios are the 2 degrees stabilization and the 4 degree stabilization shown here, but we did some extra ones trying to see whether we can again capture the bifurcation point. And yes, indeed we did. We do have it in this simulation, both actually the CMIP scenarios and the CMIP scenarios. And on the right, you can see how we estimate the probability of collapse of the AMOC, shown here on the right-hand side, on the right axis, versus the variance of the sea ice transport across the Denmark Straits, which is our, let's say, indicator of an AMOC tipping in our model, in this model. And we see that in the bottom axis is emission level, or temperature, because CMIP is in global warming levels. CMIP is mostly on levels of emissions, but there is obviously comparison between the two. If you translate the warming levels into the emissions levels, then we can estimate that in both cases we see that opening of the window, as we call it, of opportunity for AMOC to collapse much earlier because of the internal variability. At very high levels, obviously, of emissions, the AMOC will collapse, and beyond, at 4 degrees, it does collapse. But there is a probability, meaning ensemble members, I express the probability as ensemble members where it collapses versus the total ensemble members that we run. And we see that there is a probability in both simulations for this to happen. And it happens in the same range of emissions, in the same range of temperatures, approximately. But there is rate dependence. And that rate dependence says that in the faster scenario, which are the blue dots here, apologies, I didn't mention it on the plot here, but the blue dots correspond to CMIP, which is a faster forcing scenario, and the CMIP are the purple dots, and they happen a little bit later, not dramatically later, but distinctly later for all the cases. So there is a rate dependence, meaning that delayed mitigation might lead to tipping, and that tipping, and it depends. That tipping depends on how fast we reach that point of delayed mitigation. The fastest emissions, the fastest warming scenarios move the window more to lower temperatures and to lower emissions levels. And so, and you can see that compared to Armstrong-McKay's paper, which predicted that the AMOC would collapse at 4 degrees and above, we find that this can be much earlier due to extreme events in the subpolar gyre, even down to about 2.3 degrees Celsius. All right, so now we have been looking, I have been showing you a lot of results from numerical models. And we understand that if we want to borrow terminology from dynamical systems response, then we are looking at abrupt nonlinear forcing, much faster than the forcing changes in our system. That's what tipping is. So tipping is what we see here in this green line, not just a linear response to forcing, but the abrupt change. But the question is whether we can do in numerical models what we call rate-induced or noise-induced instability. And what is the predictability of such kinds of tipping? Because if there is, as the GIS model shows, rate-induced or rate and noise-induced instability together, that opens the door to reassessment of tipping thresholds and timescales for their occurrence. And so it is very important to include in predictability studies exactly the role of internal variability. Now, so dynamical systems critical slowdown theory is the tool that we are using to look at early warning signals and approach to tipping. And there has been tremendous work being done in this area. However, there is a question how much this type of dynamical system theory can, and I'm talking to the experts here, so I would like to hear how it can capture this interaction between extreme events and tipping. So on the left-hand side, let's take one step at a time. On the left-hand side, you see a paper. There have been a lot of papers actually, but this is one paper that I picked out, which is looking at how machine learning and deep learning can actually reproduce out of distribution gray swan tropical cyclones. And this is the black lines in these diagrams. These are all tropical cyclones in different basins: the West Pacific, the North Atlantic, etc. And you are looking at the dark lines here. The black line is the error reanalysis. And then the blue line is one type of deep learning emulator that they used, and they managed to approach much better than, for example, other more conventional machine learning techniques. It doesn't matter, but the important thing is that they are doing pretty good job at simulating at least these types of extremes in the system. We also have built an emulator of the NASA GIS climate model, which is actually trying to emulate future projections after being trained on high and low scenarios, whether it can predict the distribution of extremes and the trajectories of extremes and the spatial distribution of extremes in the system for any scenario. So you don't have to rerun the model for any custom-made, whatever thought experiment you have, but you can use the emulator, which has been trained on simulations, so it is a physically informed machine emulator. You train it into you train it by the scenarios, and then you let it reproduce the distribution of and the pathway of extremes in the future. And they are doing, and we are doing a pretty good job, at least in terms of, for example, the intensity, which is shown here. We predict the 245 pathway trajectory of extreme events, heat waves in the model globally. The gray lines are the training, the 126 scenario and the 585 scenario, and we can predict 245, but we can also predict other scenarios as well, more or less. And that is a very simple emulator that we use here. It's a very early study. Of course, we can do much better job. Okay, so we can use deep learning to emulate weather extremes. But can we use deep learning, and how useful is deep learning, for example, to predict early warning signals and tipping points? And the studies which have been done, especially the Huang et al. Study 2024, which I think is coming from your group, showed very nicely that some of the critical slowing down based indicators are not able to distinguish some cases of noise-induced tipping from no tipping. And deep learning methods, and this is the example here, they looked at different types of idealized experiments of tipping. The red lines are the tipped members, the blue lines are the non-tipping, or I might be saying it vice versa, I'm not sure. And the idea is that you have here that in different systems, and the variance and the autocorrelation, for example, are not able to capture that tipping. But this deep learning algorithms are doing a much better job, and they are even giving information about early warning. So this is interesting, particularly interesting, as I showed before, particularly in the case where we have overshoot scenarios. Overshoot scenarios are combinations of rate change and noise, obviously, instability is in the system change. And so when we are looking for tipping, particularly related to extremes, rate-induced and noise-induced instabilities are very important. So I'm concluding, and I have no idea what the time is, but the take-home message that I'd like to convey is that continued warming, and particularly, and in particular, accelerated warming, will bring upon us unprecedented extremes. We've seen this in East Antarctica and West Antarctica. We've seen this in the Arctic a lot. And we project it in numerical simulations happening. And that means that it will probably, and at the same time, it will bring us closer to internal critical thresholds. We don't know where they are for sure, but they are there, and we're getting closer to them. So whether the question is whether these unprecedented extremes can push us faster to these thresholds. Both these will interact and possibly lead to tipping behavior earlier and on smaller and large scales and globally. And these interactions are unavoidable, obviously, since extremes are unavoidable, and are currently understudied. Machine learning provides a possibility to address nonlinear and rate-dependent tipping trajectories. And the open questions we have is, can we extract early warning signals from the behavior of extremes, and in order to anticipate tipping points? Can we monitor extremes sufficiently? What type of observations do we need to have in order to monitor those extremes which can lead to tipping if they exacerbate? Do we need satellites? Do we need reanalysis models? Do we need machine learning? Rate and noise-induced instabilities are very important, and they should be looked at with any tool we have, including, of course, deep machine learning. And we need to be monitoring extremes with more focus to those which are lead to tipping as well. I mean, obviously to all of them, because they are all detrimental, but obviously the ones that are tipping the system are the ones which are the interest of this talk. Okay. And thank you very much. This is work that has been inspired by the ClimTip and CMIP efforts. I'm very, very lucky to have been part of these groups and learn from you. And of course, it has been supported by NASA of previous years and the climate modeling group at GIS, a big shout out, whose work has gone into all the simulations that I showed. Thank you.
Thank you so much, Natassa. Thank you. We have, it's a lot of diverse type of literature and research that you covered. I hope we can take on these questions. We have a few in the chat, but also those who asked these questions, you feel free to unmute yourself and ask them. Otherwise, we could also read them. Perhaps anybody else has questions. Should we start?
Sorry, yeah.
Go ahead, please.
I have a question to these early warning signals.
Yes.
I don't know if you could put up the slides with the three different.
Yes, let me share again. Of course, the questions can be addressed as well to the group there.
Right.
Yeah. So just an open question then.
Yes.
Yeah, that one there. So I'm just wondering. Yeah. So the similar system to the left with the saddle node, which is sort of what we know a lot, is that if you have a noise, so the red is, I mean, you had it's an R tipping. You don't have a noise induced tipping scenario.
No, actually, what they are doing, and people can correct me, what they are doing here, they do have a rate change, but they also add noise to the system.
Yeah, obviously, because the warning comes from how it reacts to noise, right? The
Yes.
loss of resilience, and that, I guess, it goes for all the cases. Okay, so the reason I'm asking is also that if you have more extremes, I mean, you could have, say, a more intermittent distribution with more extremes, but the sort of average noise would be less intense. So I'm just wondering if one could say anything. It's probably it's not your expertise, but that could also lead to less probability of noise-induced tipping, even though you have more extremes. Unless, of course, it's the situation where you have like very extreme, like we've been looking at alpha stable noise, where sort of single events would tip you over. But that seems to be a very unlikely situation.
Yes, so if we borrow from the observational evidence, extremes, for example, that are happening, and compound extremes, particularly that are happening in like the Amazon area, this is like the type of extremes that we are talking about, the ones that are very well outside, like 2, 3 and above the standard deviation. So these extremes can, and especially if they're compound, and if they increase in frequency, the system is not able to recover from these changes. So that in that sense, they can lead to tipping. Now, they are expressions of internal variability because they're not happening they're not happening every time. They can be exacerbated, for example, by continuing ENSOs or longer ENSOs or multiple and triple ENSOs that are happening and so forth. And they can be, and also we know that with global warming, the extremes are shifting. So the distributions are becoming redder. And so I think that this is the point that I'm trying to make with regards to how the noise in the system, which is of course modulated by warming, can lead to tipping. Whereas, for example, if you consider the average, you don't consider that, you don't take into account extremes, then and look at the ensemble mean of the simulations, for example, you'll never see that bifurcation, that ensemble splitting. Some people call it ensemble splitting. Nowadays, people have been looking for it, and we've seen it happening in, for example, the GFDL model. We have seen it happening in our model and in some lower complexity models and so forth. So it is something that it's out there. I don't know if we model it appropriately, if we model it appropriately. And I'm not saying that our model, what it's doing, is exactly how the nature behaves, is realistic. What we're putting forward is a possibility for something like that to happen.
Maybe can I just add 2 words there, because I think, Peter, you're hinting at a very important point. So in the plots that you saw, we're using white noise forcing and basically pushing the system towards the critical rate, and then sort of the noise decides whether they tip or not. That's sort of what that you spotted that correctly. Now, if you don't use noise forcing, in principle, if you want to extend this from sort of like conceptual proof and sort of extend this towards AMOC in reality, then you would need to train such a model using noise that is realistic, sort of using the type of noise that we expect, not today, but that we expect to would occur in the future, where the AMOC is sort of at a sort of higher risk of tipping. Meaning we would need to include these sort of, really extreme events, maybe events that are sort of outside the observational distribution, compound events. I think sort of the hint that you gave towards Levy stuff isn't as unrealistic as one might think in the first place. But of course, in the end of the story is not to train the model sort of on, again, sort of conceptual models forced by Levy noise, but to somehow get an actual representation of the noise, maybe just sample it from the climate model projections and just use that. So I think that, very good comment.
I suggest we move on to the questions in the chat, right? Because there are quite a few. There is a question from Steffi and Libera asking what is Grey Swan tropical cyclone events? And another one from the same person, why is that the GSMs simulate lower variability while ML models get the extremes and higher variability better? There's also a related question to clarifying the conclusions of that paper. They're asking if they are right that the main conclusion of the ML-based prediction of the Grey Swan paper was that if degree 4 or 5 tropical cyclones are removed from the training dataset, the ML model stands no chance of predicting them.
Yeah, okay, these are very good questions. Okay, so again, I'm not an expert in tropical cyclones, so but I will give you my understanding of that research. So the Grey Swans are the events which are above 5, category 5, and they're very rare, but they happen. And what they claim in this paper is that if you have a machine learning system, a machine learning algorithm or system which you train on tropical cyclones wherever they happen, it learns the relationship of the underlying conditions. Thank you, and it will identify them even outside the geographical region where it learned it from. So conditions, for example, as we see conditions changing across the globe because of the changing in the background state, conditions which were found, for example, in one particular location may be now applicable further to the north. And if you were training the emulator within that particular region, you will never get them. But because you are using a more broader training set in different locations, you can identify them. And so that's their explanation of being able to capture these events. Now, machine learning doesn't suffer from some of this type of machine learning doesn't suffer from inherent issues that climate models have, meaning we average a lot on spatial scales and temporal scales, and our forcing is also we'd never have the full forcing because we never have the full set of aerosols and greenhouse gases and all the interactions. We never capture them. But the machine learning, because it captures phenomenology between relationships from different drivers, it theoretically has all this knowledge in it. Of course, it has other drawbacks and suffers from other problems, machine learning, deep learning estimates, projections. But of course, in this particular case, and in general in weather modeling, machine learning is taking over very, very fast compared to our two mathematical models, PD-based models.
Thank you.
Because I asked the question, can I just say one thing? That yes. If I remember, I'm also not a deep learning expert, but if I remember correctly, the paper indeed said that if you remove tropical cyclones above degree 3, which means 4 and 5, from, Pacific Ocean, and if it's already in Atlantic, it can kinda understand that, I can generate it over Pacific too. But if you completely remove them from the training data set, at least their conclusion was, at least I think the plot that also you showed on the slide was clear that they stand no chance. And that is for me a little bit worrying, that because particularly for extremes, they are by definition, I would say, I think our Well, most important or most interesting question is that, well, they are completely out of distribution of our current and past climate in a way. Yeah, that's why I asked.
Yes, I see your point. Of course, if we, of course, we will. You cannot train outside of distribution completely for black swan events, and so I think that there are limitations there too. And maybe perhaps approaches which are being developed right now are with physics-informed models, for example, where they can look at drivers and project the drivers change. Yeah, it's an evolving, very quickly evolving field. But at least what they show is that with gray swans in particular locations, and that was only tropical cyclones, right? We are not talking about heat waves and other more complex or different types of events. So, yeah, thank you.
Thanks. There are more questions there in the chat. One clarification asking, sorry, right here. It asks if you could explain which exact mechanisms caused the collapse of the Conger Glacier.
Yeah. Yes.
And
So the Conker Glacier was already ice sheet. It was also already destabilized somewhat, but was not anywhere near tipping at the time where these events happened. And it was a month of several weeks, actually, where there was a heat wave and an extreme atmospheric river that happened over the area, brought immense numbers of precipitation and snow. A big part of the precipitation was not rain, it was snow, actually, but which melted very quickly by the extreme heat. And that water went into the glacier and structurally broke down the system. So that left and that expedited the collapse. It wasn't the one. The paper says clearly that it wasn't what drove the collapse, but actually it was the one that expedited it, pushed it further, much faster.
Thank you. There are two related questions, I think, unless I understand. One from Juan, they're asking if you can discuss a bit more on SPG behavior during AMOC collapse in the slide of mitigation and climate intervention pathways.
Yes.
And another one from Colin says, the TIPMIC protocol includes negative emission pathways as well as zero emission runs. If there are model members where the AMOC tips before the negative emission runs start, does the tip recover the NE runs?
Yes. Actually, Colin, this is a very good question. So where we have the bifurcation, the scenarios where we found the bifurcation, we didn't do the negative emissions. We should do them. I agree. It's a very good question. Because of computational limitations and political limitations. But yes, so we should do it. The other thing is that the GIS model, and maybe should I share again? Well,
Yes,
the GIS
yeah.
model has this behavior where it will collapse in here. So, oh yeah, that's
We
not
can see
the
it.
figure. Yes, but you cannot see the behavior that I was wanting to show you. What happens is that so this is TIPMIP here. This is the 2-degree scenario. This is 2.5 and 2.7. This 2.7 we see it very clearly. That's the scenario here, and this is the 3, and this is the 4 scenario. In the 4, we have a collapsed AMOC, and after 3. Most of the ensemble members, as you see, they are collapsed. So I expect that everything between 3 and 4 will have no bifurcation. Will be like pretty much like the AMOC is collapsed. So the AMOC in the GIS model collapses at high levels. We've seen it in 585 and in the 370 scenarios, SSPs before. So it would be, interesting to extend perhaps these scenarios to see what happens after the negative scenarios. For this scenario, though, but we did and we've sent you the data, actually, the AMOC does not recover. And the interesting thing, if you want to know more about this, because it's extremely interesting, is in the ramp down, the 2-degree scenario, in the 2-degree warming world, right? We get 2-degree temperature in the stabilization after the ramp down from 4 degrees. Again, the AMOC does not recover. And yet we achieve a 2-degree stabilization. I haven't looked at these runs yet. Someone needs to help because we are only 2 people at GIS left looking at this. So
thank you, Natassa. We have more questions, but we're officially out of time. Although we can
I'm
stay,
happy to stay.
and people who are happy to stay, we can then cover the other questions.
Sure.
I don't know if you see them in the chat, but I can also read them for everyone. So that was on the SPG AMOC collapse in TIP-MIP, and the other, ZEC-MIP, right? And then there's a question about the increased noise in the context of changes in the mean state and among multiple components of the climate system. Can increase the probability of a transition from one stable state to another?
Yes, so it can lead. That's what our model has shown, but also that's what from observations where we see, for example, what happens in the Amazon, where like a compound extreme, that noise can lead to a state change, and in our simulations. Are there warning signals? Yes, so that's part of the same question. Yes, we are looking. That's the $1 million question, right? But we know that the indicator, because we know what is the driving process in a model, is the sea ice transport, which has increasing variance, and that increasing variance, which is slowly increasing, is from 0, where the AMOC is healthy in all ensemble members, as we go to the higher levels of forcing, then that variance after 100 years, the variance of the sea ice transport after 100 years has increased. Maybe that could be the indicator. We are thinking that is the indicator. At least the diagram that I showed before shows exactly that. Again, I don't know if I'm not claiming that this is a realistic process that could happen in the world, and I'm not saying go out and measure the sea ice transport through, but maybe we should look at this a little bit more.
Right, I think Peter Ashwin is not sure if he's in the room, but he wrote this comment here, right? Very interesting discussion. And he's writing with Paul Ritchie and Sneha Kachara that is almost ready.
Yes.
And it tries to tackle a problem of what might be the ingredients of a skillful warning of R-tipping.
Yeah, that would be extremely interesting. I follow some papers that they have from this group, and I think it will be, very, very interesting to see that work. Look forward.
And then the last question there is from Tommaso Alberti, also about real noise, something about that Nicholas commented on. Do you see it? One of the properties of extreme events is that they are not noise, but occur on fast timescales that can be separated to the large-scale ones. Have you tried to detect transitions at different temporal scales in your models and not only overall?
No, I have not. And I would be very interested for someone to tell me how to do this and help us do it. But I really think that we can analyze more of that behavior. But as I said, again, we always have to keep check on ourselves how realistic something like that is. Yeah.
I had one question because I just marked it for myself. Because could you talk about the significance of your finding? Remember what you said compared to the Armstrong-Mackay's paper about AMOC collapse around 4 degrees versus what you found around 2.3, 2.7. How has, I'm not sure if this message has been kind of like communicated widely, and was there press on that, and what was the...
No, it was not, because again, it is one modeling study. And of course, our model is the only model that has this bifurcation. What can we do? But it's the only, it was only a modeling study. And it is, as I said, again, there are obviously a lot of, we cannot place much very high confidence on this. I understand that, but at the same time, what the connection I'm trying to make, and maybe we should make it a little bit more clear and try to investigate similar cases. Try to promote. There are people who put added noise into the system, and they saw it. There's the CMIP paper from Italy, and then there is the paper, as I said, Rake Borner's paper as well. The people saw these transitions happening, and at the same time, we have the evidence from observations where, even though we consider that ice sheets will collapse at above 2 degrees, yet today we see big chunks cutting, like collapsing at lower temperatures, slightly lower temperatures, and so I think there is a kind of plausibility in these findings, that I wouldn't put the highest confidence in them. Yeah.
Okay. Yeah, thank you so much. I think that we covered all the questions that were in the chat. Yeah, I would like to thank you again, Natassa. This was really amazing, and thank you so much for taking up our invitation.
Thank you.